Hello, folks. Long time no see. It's been a while, actually. I have not uploaded a single video in 2023, I think. Maybe one, maybe none. So I will be more active moving forward. So stay tuned for that. I have a few ideas. One of the ideas is to implement a tensor library from scratch. I'm thinking about doing that in Rust, so Rust programming language. Or perhaps in Python. So I have a few options on, I think, what programming language I would want to use. So I also want to make it fun. So it has to be fun, right? So I think these videos are also fun for me. It's not, I guess, only fun to you. If it is, I hope, fun to you. But yeah, so other than that, please feel free to make suggestions in the comment section below. So that's below the video, I guess. So I cannot promise I'm gonna be able to do everything that you suggest, but if there is enough interest, I'm down doing fun things with implementing software and implementing AI ML methods. So I think a lot of exciting stuff is gonna be coming soon in a way, right? So perhaps a series of videos or playlists, if you want to call that. I guess on YouTube that's a playlist. So yeah. But today we're going to be implementing principal component analysis. So that's PCA. We're going to be implementing that from scratch in Python. I will be using NumPy though. So that's one dependency that is very useful because it has a lot of vectorized linear algebra operations. We could do it in plain Python too, but as you know, that's going to be slow. So, and on top of that, we have GIL, global interpreter lock. So I don't want to deal with that. Anyway, so let's go ahead and do that. Okay, so I have prepared the evaluation code in advance. So once we're done implementing PCA, we're going to go ahead and test it. So we have that. Now, I hope that you do have some understanding of PCA. It's not necessary to know how to implement, PCA and all that, but at least some understanding would be very, very helpful. So yeah. And as you know, I will still go over PCA briefly. So don't worry if you just don't know anything about it, I guess. So let me reformat this thing. I mapped it to, so that's F, colon F, whatever you want to call it. And okay, so it exceeds. I have this 100 line or 100 character limit here. I don't want to exceed it. It's not a very hard kind of a religious rule or something, but still. Okay, so all right. So what is PCA? Now PCA, as we know, that's a dimensionality reduction method. The idea is that we have some data, some set of features, and we want to reduce the number of dimensions in these features. Okay, so kind of sensible thing to do, right? So sounds reasonable. I'm not going to go into the curse of dimensionality, but basically, a lot of times you do want to reduce the number of dimensions, right? You do want to do a dimensionality reduction, and PCA helps us with that. Now, to understand how PCA works, let's think about how one would want to go about reducing number of dimensions. Okay, so let's say we have some data. Okay, so we have data, and we want to reduce the number of dimensions. Okay, so data here, you can think of that as a collection of features, and every feature has some number of dimensions. Okay. And the end goal is that every feature would have less dimensions. Okay, and if makes sense, right? So that is the goal. We have some collection of features, say n features originally, and we want to have still n features but less dimensions. So originally perhaps we had m dimensions. Now we want to have m over 2 dimensions. I'm just making up the number. Doesn't matter. Okay. Now, of course, we also don't want to have a significant or some bad information loss, right? So we would hope that even though we reduce the number of features, we still retain a lot of information, and perhaps we do it in a way that we can at least approximately reconstruct the original data. Okay, so some approximate reconstruction. If I can get that, I'm cool with that. Okay, so that's actually what PCA does, right? So what it does is that it does what I just described. So it reduces the number of dimensions in a way that you can then reconstruct it and so forth. But does it by projecting the original features onto directions that maximize variance. Okay, and in terms of this maximizing variance bit, you can think of it as like the components, or components that maximize variance. Perhaps they are, the way you can think of it is that these components, they are what makes some of the features in a collection of numbers, and these components that have higher variance, they make up most of the information. You can think of it that way. And so we want to retain the components with highest, with maximum variance. And when I say components, that actually is the number of components. So how many components do we want to retain? If you want to retain all the components, then, well, you're not going to have any dimensionality reduction, right? So you're going to retain some number of components, and that's one of the parameters. And there's another thing, standardize. Standardization is, of course, different from normalization, but normalization is a vague term. So depending on domain, depending on a field, you're going to see different definition of normalization. What kind of normalization is it, right? So is it RMS normalization? Is it some, standardization in this case, actually, some people also call this z-score normalization. So many different definitions. But in this video, we're going to be more, precise with the definition. We're going to say that standardization is an operation that transforms the data, so the input features, data here is input features, in a way that across the feature dimension, or the feature axis, we have the mean of 0 and the mean of 0 and the variance of 1. So 0 mean, unit variance. Okay, so let's go ahead and implement this now. I'm going to add a simple doc string, just in case. I don't know. So let's do something like performs dimensionality reduction via principal component analysis. Okay. All right, so let's go ahead and implement this now. The first step is standardization. Now, standardization is not needed if the data is already standardized, so it's like a flag. It's a formal parameter here, right? So if standardized is true, and by default it's true, so we're not going to assume that the data is standardized. If it's not standardized, well, we're going to standardize the data. So we're going to redefine it as basically we center and then divide by standard deviation. So this operation here, that's centering the data. You subtract the mean, and we do it for every feature. And then for every feature, we divide by standard deviation. Of course, that is basically z-score normalization, as I said. We're going to call that standardization. Okay. Now, I've talked about variance. So where do we get this, variance for these features and so forth? Well, that comes from the covariance matrix. Well, I think NumPy doesn't have this. Torch does. So PyTorch does. Have to do it this way. Okay. So we find the covariance matrix. We compute the covariance matrix. And the next step is to do a eigen decomposition. Well, there are two ways. Well, there are at least two ways to do this. Okay, there are perhaps other ways as well. But in this video, I want to show you eigen decomposition method. So this could also, PCA could also be implemented using SVD. So that's singular value decomposition. But yeah, so in this video, I think I'll be doing eigen decomposition, and perhaps in the future, I'm going to do SVD if there's enough interest. Because again, so PCA can be implemented using either of these two methods, and there are other methods as well. But these are the ones that are more, I guess, well known, or more commonly. You're going to encounter these more commonly in the wild. So yeah, so let's do eigen decomposition now. So we're going to get eigen values and eigenvectors, and in NumPy we have the linear algebra module in a way, or a sub-library, whatever you want to call it. And there we have eigh, so that's nice. We're going to do cough. Okay. Now the next step is we want, again, the components that maximize variance. So the way we're going to do this is that we're going to sort the eigenvalues. And to show you the sorting functionality that NumPy has and we're going to be using, I just launched IPython interactive shell. And so let's have some numbers. Let's say I have nums, and okay, that works actually. 3, 1, 2. Okay. Maybe it's better to do some like 12, 4, and 1. I think that just highlights, will highlight, or make my point basically. So one way to sort numbers is, I mean, you can directly sort it, so you can do whatever, sorted nums. But that's not what we want to do here. So we're going to use NumPy because of the benefits it provides. But so there is also a function called arcsort, and we can do that. So arcsort, what it does is that it returns the indices such that if you were to arrange numbers according to these indices, you would get the sorted array. So you would get a sorted tensor. So as you see, if I index into nums with arcsort of nums, that's going to give a sorted tensor. Now, the way we're going to do it here is that we also want a reverse of this, because we want the first however many components. So n components is the parameter for that here. But we want to have first n components. And to do that, we can also we need to basically reverse this. And in Python, there is a reverse operation. So you could do something like, if you had a Python list like 1, 2, 3, you could have reversed that by doing reverse and then list. Okay, reversed. Okay, but this is on. It actually pretty much well, it reverses. It constructs a new list in a way. You can think of it that way. Now, NumPy supports what's known as a view. And a view is, you can think of it as a way to look at the data. Maybe I'm going to make a video on views. So there's this other way to do this in NumPy. Now in Python, there is also we also have this operation here, but that also creates a new list. But in NumPy, it doesn't really create a new list. Again, it's just a way you look at the tensor, right? So you don't really need to copy over the things. So this is O1 operation right here. That's O1. Now, arcsort is n log n because that's sorting. Okay, I think by default it uses quicksort. I don't remember. We're gonna have to check, but that's n log n. But this one here is the O1 operation. So that's what we want to do. We're gonna go ahead and now do the get the indices. That's going to be eigval. And then we can do it this way. We can arcsort this, do -1, and get however many components we want to get. And then we redefine these. So eigval at index and eigvec index. Okay. And then the features that we get, it's just the data by the eigenvectors. And we return the features the eigenvalues and eigenvectors. Eigenvectors here, they're going to be useful if you want to reconstruct the original data. So we're also going to return this. So to go over this algorithm once again, we have some input data. We first standardize that, if it's not standardized. If it is standardized, then you can manually specify standardized false. You don't need to do that over again. We then compute the covariance matrix of the transpose of the data. Well, that will be needed. And then we get the eigenvalues and eigenvectors by using the eigh function that can be found in the NP-linalg module or submodule. After that, we want to get the components that maximize variance, or those that have the highest variance, and we do that by sorting eigenvalues in a reverse order. Well, doing arcsort. Arcsort provides indices, reversing these indices, and then getting the top n components number of those. So if n components is 3, we get top 3. And then we get the eigenvalues and eigenvectors. So eigenvalues are going to be sorted or rearranged or obtained according to these indices. And then eigenvector, we're going to get all the rows, but the columns, those are going to be, or you can think of the in a way a second dimension. Those are going to be extracted according to the indices. Finally, we get the reduced features. That's just data by eigenvector, and we return everything. Now, I said I do have the code for testing or evaluating this, and I do. So we're going to be testing this against sklearn's implementation of PCA. So there, we still have n components. I initialize just some random numbers, so those don't come from Gaussian distribution. So we don't have a mean of 0 and a unit variance or something like that. So we go ahead and do the standard scalar fit transform. And this out is basically reduced features here. And fit here is reduced features using our implementation, our NumPy implementation. Okay. So then we have the standardized features. We standardize it manually here. The reason I have the standardized features is to then test the reconstruction as well. Because the reconstruction really, what that would do is that it would reconstruct the standardized data, would not reconstruct the data before, although we could also kind of revert back if we wanted to. And so we're just going to do out and feet. We're going to do NP all close, so that basically tests or compares out and feet and make sure that they're close enough. Okay. Same goes with NP all close. Now, sometimes with some out and feet, some I guess not necessarily out and feet, but the data sometimes because of the numerical issues and the way sklearn does PCA and we do PCA, there might be numerical kind of precision errors, and you might not get things to line up exactly, but they'll be close enough. So we would hope that both of those return true. So let's go ahead and test that. So Python PCA. Do I have that as a... Well, both of those are true. Do I have this as a... Oh, I don't. So yeah, I made it made PCA Py an executable, so it's I don't have to type Python. Okay, so we get true for both, so that's great. I also have a random seed, whatever, 1, 2, 3. Now, even with the eigen decomposition implementation, there is another way, more efficient way to go about implementing this. Okay, as I told you, arcsort is n log n because it relies on So it uses quicksort, so that's n log n, but there is also merge sort, but that's also n log n. Heap sort, that's n log n. Anyway, so this is n log n. Okay, so this operation right here is n log n. Now, can we do better? Okay, and the answer is yes. But for that, we have to understand how eigh works, or the requirements of eigh. Okay, so now eigh is again a function, and what it does, that computes the eigenvalues and the right eigenvectors of a square array. So in terms of the requirements that eigh imposes onto its input, not much. It has to be a square array, but that's pretty much it. So it's a kind of a general function. You can use it for all kinds of square arrays. Okay. Now, if you look into NP-linalg submodule, okay, you're also going to find eigh. Okay, let's look into that. Okay, eigh is a bit different. So returns the eigenvalues, or return the eigenvalues and eigenvectors of a complex Hermitian, conjugate symmetric, or a real symmetric matrix. Okay. Now, this is it has more requirements, but eigh itself is a bit more efficient because it expects a very specific kind of a matrix. Okay, it's a Hermitian, that's same as a conjugate symmetric matrix or a real symmetric matrix. Okay, but so it's a bit more efficient than eigh. You can think of it that way. But in addition to that, it returns the eigenvalues in the ascending order. Okay, but of course that was not the case with eigh. But this is the case with eigh. But now let's look at what we're doing here. Well, we're sorting things just because we want to make it so that eigenvalues are in descending order. Now, eigh already puts them in the ascending order. So eigenvalues, by default, the way it returns eigenvalues, those are in ascending order. Okay. Well, then it just makes things very easy. It's already sorted. All we need to do is kind of look into this in a reverse, from the other side, basically. Do it in the reverse order. And I'm going to show you how to do that. So we're going to comment this out, and instead of doing arcsort, which is n log n, we're going to do a range. That's O of n. Okay. What we're going to do is we're going to say length of eigenvalue minus 1. So we walk backwards. Length of eigenvalue minus 1 minus n components. And again, so we walk backwards, so that's minus 1. Okay. So these two lines are in a way equivalent in terms of what they produce. But if we run this, so get both true. Now again, so if I were to comment this out and just change it back to eigh, that works. Of course, if I change it to eigh, that will still work. But it's just an overkill here. Like, why are we doing arcsort? So if we use this, or it still works. Now I'm running this inside NeoVim. That's why I mapped it to Control Enter. So, but let's rerun it here as well, just so that we're consistent with this testing. Of course, we don't have a lot of tests, right? But still, so that's the PCA. That's the principal component analysis. So if you have any questions, feel free to comment in the comment section below the video. But with that, I'm going to see you next time.